Welcome back to Distributed and Multi-GPU Deep Learning. In this video, we're talking about the high-level API for distributed training in Keras. So we'll be talking a little bit more about the high-level API of TensorFlow, Keras, and how it supports distributed multi-GPU training. Keras multi-GPU and distributed training. Use the TF Distribute API to train Keras models on multiple GPUs. With minimal changes to your code in the following two setups. One, on multiple GPUs, typically 2 or 8 on a single machine, that is actually a worker node with a single host and multi-device. This is actually the most common setup for researchers and small-scale industry workflows. Or on a cluster with many machines, but that means multiple workers, each hosting one or more GPUs, multi-worker distributed training. This is a good setup for large-scale industry workflows, that is the training of high-resolution image classification models on tens of millions of images using 2 to 100 GPUs. So this is a large number of GPUs. They cannot be squeezed within just one single host machine. So a single host multi-device or multi-GPU synchronous training. In this setup, you have one machine with several GPUs on it, typically 2 to 8. Each device will run a copy of your model called the replica. For simplicity, in what follows, we are assuming that we are dealing with 8 GPUs with no loss of generality. Here's how it works. At each training step, the current batch of data called the global batch is split into 8 different sub-batches or local batches. For each instance, if the global batch has 512 samples, then each of the 8 local batch will have exactly 64 samples. That means 8 times 64 will give you 512. So we basically divide it into equal numbers for each of the local batches. Each of the 8 replicas will independently process each local batch. So one local batch is assigned to each of the 8 replicas. They run the forward pass and then the backward pass and output the gradient of the weights with respect to the loss of the model on the local batch. The weight updates originating from the local gradients are effectively merged across the 8 replicas. So this is where they sync them together. Because this is done at the end of every step, the replicas always stay in sync. In practice, the process of synchronously updating the weights of the model replicas is handled at the level of each individual weight variable, and this is done through a mirrored variable object. So in terms of the code, this is how you do this. To do a single host multi-device or synchronous training or multi-GPU synchronous training with the Keras model, you would use the TF Distribute Mirrored Strategy API. And here's how it works. You initiate the mirrored strategy, optionally configuring for the specific devices you want to use. By default, you would use all GPUs available. Use the strategy object to open the scope, and then within this scope, create all the Keras objects that you need to contain the variables. Typically, this means creating and compiling the model inside the distribution scope. Then do the training by calling the fit function as usual. Importantly, we recommend that you use the TF dataset objects to load the data in a multi-device or distributed workflow. Here's what the code actually looks like in more detail from what we covered previously. So you create the strategy using the TF Distribute Mirror strategy. Then with the strategies.scope, you then compile the model, create the model and then compile the model. Then you call the fit function on all the available devices that you want to use within this scope. Then finally you call test or evaluate the model on the available devices. The previous case was actually suitable for small-scale workflows. So if you have a need for a larger scale workflow, the better strategy to use is the multi-worker distributed synchronous training. And here's how it works. In this setup, you will have multiple machines called workers, each containing one or more GPUs. most of what happens is the same as what you did for the single host training. Each available GPU will run one model replica, and the value of the variables in each replica are kept in sync with each other after each batch of data. Importantly, the current implementation assumes that all workers have the same number of GPUs. That is a homogeneous cluster. So how do you use it? You set up the cluster, which is in the next slide. Then you can set this up using an appropriate TF config environment for each worker. This tells the worker what is his role and how to communicate with his peers. On each worker, run your model construction and compilation code within the scope of the multi-worker mirrored strategy object, similarly as what we did for the single host training. Run the evaluation code on the designated evaluation machine. So in the multi-worker case, we need to communicate over the network. So first you need to set up the cluster of machines. First, set up the cluster of machines. Each machine individually should be set up so as to be able to run your model. And each machine will typically run on the same Docker image and be able to access your data source. We need to set up the TF config environment variable. While the code is running on each worker is almost the same as the code in the single host workflow, except for the TF distribute strategy, there's one significant difference between the single host and multi-worker workflow, and that is that you need to configure the TF config environment on each machine running on your cluster so they know about each other within the network. The TF config environment variable is a JSON string which specifies the cluster configuration, the list of addresses and ports of the machines that make up the cluster, the worker's task, which is the role that specific machine plays within the cluster. So the example down here. In the case of a multi-worker synchronous training setup, we need to assign different roles to the machines who are workers or evaluators. For example, if you have 8 machines with 4 GPUs each, you will have 7 workers and 1 evaluator. The workers are the ones that train the model, each processing sub-batches of the global batch. One of the workers, the worker 0, will serve as the chief. It's a particular kind of worker that's responsible for saving the logs and checkpoints for later use. The other workers are which are not the chief. They would actually basically work similarly, and they do the processing of the sub-batches of data. Now there's one node that is actually working as the evaluator. So the evaluator runs a continuous loop that loads the latest checkpoint saved by the chief worker, runs that evaluation on it, and it does it asynchronously from the other workers, and then writes the evaluation log. So there's one that's acting as the chief to coordinate the checkpointing, and there's one worker that's basically acting as the examiner, right? It's the evaluator that runs continuously to check on the output of the data of the other worker nodes. You will run the training code on each of the worker, including the chief, and the evaluation code on the evaluator. The training code is basically the same as what you would do on a single host setup, except that we use the multi-worker mirror strategy instead of the mirrored strategy. The evaluator will simply use the mirrored strategy since it's running on a single machine and does not need to communicate with other machines, and we will just call model.evaluate. It will be loading the latest checkpoint saved by the chief worker in a storage location and save the evaluation logs in the same location as the logs of the chief worker. So this is what the code for the main worker, the worker 0, the chief, looks like. So at the front, we have the environment variable set up with the cluster configuration, which are the hosts, which are the workers, and then the task that we are performing. And in this case, we notice that we have this index 0, which means that this is the chief. And then we actually run the strategy, and the strategy we are using is the multi-worker mirror strategy as mentioned before. And with the strategy scope open, we then create the model. We do the model compile, the model creation. Now, if the model has been saved into a file earlier through a checkpointing mechanism, then we can restore it from the file. Otherwise, it will be compiled from scratch. And then it's saved into the model. After doing this, we will then call the normal fit function to do the training. So in order to do the training with a certain checkpointing, we will set the checkpoint callback in here, and then you point it to where you actually would save the checkpoint file. So remember, the chief is responsible for checkpointing and saving the current configuration so that it can be restored later. So that's why we have the checkpoint callback set here for worker 0, and we can have some monitoring using the TensorBoard as well. Then the next function is basically the normal fit function with the training data and the callbacks being assigned. So this is for the worker 0, which is the main worker that actually does the checkpointing action, and the other workers are mainly doing the training only without the checkpointing. So it does also, the worker 0 also does the fitting or the training as well as the other worker nodes that we are using. So for the other worker nodes other than chief worker node 0, we notice that we have this configuration as well. So we have to set the worker index, which worker is this, and then we in the configuration file we set the cluster, the different machines, and then whether or not this is worker 0 or is worker 1. So this is worker 1 in this case, and then we set the strategy, the mirror strategy. We open the scope, and then we basically make or restore the model as before. And we have the checkpointing code here as well, but in this case we shouldn't be doing this, and we are saving it in the local location rather than the global location, which actually stores the full backup for the entire model. So this is actually a local path because we want to just store a backup in case we need it, but the global model is being stored by worker 0. Then we call fit as the same as all the different worker nodes need to call this function in order to do the training. So we finally come to the evaluator, which is part of the multi-worker distributed training. But you notice that instead of using the multi-worker mirror strategy, it actually uses the mirror strategy, since there's no longer any need to actually synchronize this particular machine with the other worker nodes. So it's not actually involved in training, as we have mentioned earlier. So you notice that the strategy it uses is actually the mirrored strategy and not the multi-worker one, since it only needs to use the GPUs within the same local server that's being used as the evaluator. Now we open up the strategy with the dot scope, and then we restore the model that's actually been saved by the chief, right? The chief, actually the worker 0 actually saves the checkpoint containing the globally trained model at a location that everyone can access. Now this is not the local copy that may be checkpointed by each of the individual nodes. This is the global copy, the one that's actually saved by the chief, the so-called reference copy saved by the chief. So we restore this model, and once we've restored the model, we will only call one function, which is the model.evaluate. So the purpose of this particular node, the evaluator node, is only for evaluation. It doesn't call fit because it's not involved in the training in any way. Its sole purpose is only to evaluate and to check if the model that's been built is going to give you a certain level of accuracy on the validation dataset. So that's the only thing that this particular node does. So the results are of course put into a log so that you can refer to it later. So here's a quiz question for you. As before, please pause the video at the end of this question to think about the answer before proceeding. The multi-worker mirrored strategy is designed for what circumstance? A. Several workers or physical servers with multiple GPUs on each server. B. Several workers or physical servers with one GPU on each server. C. One worker or physical server with multiple GPUs on the server. Or D. One worker or physical server with two mirrored GPUs on the server. So pause a while before you proceed. And we have come to the end of this video. Thank you for your attention.